Good afternoon, Prof. Welcome to Group 20's project presentation. I'm Ryan and we have 6 members in our group including me. My groupmates are Zhiyang, Jingdao, Qifeng, Kunhui, and Lavin. Here is what we'll be going through. With the recent technological advances, the popularity of smart homes has been on the rise. To enhance the efficiency of the smart home, our group has decided to create a baby monitoring system for households with babies. Why a baby monitoring system? Well, imagine holding a baby and realizing now you have no free hands to turn on or off the light switch. Are you going to put the baby down to flip the switch? Or are you going to carry the baby to the switch and risk bumping the baby into something while you flip the switch with another part of your body? That's where our solution comes in handy. Because our baby monitoring system will have the capabilities to sense and control the lighting in the room, sense and control the temperature in the room, soothe the baby to sleep with lullaby music, and our product is better than other baby monitors that currently only has cameras to monitor the baby, with some having just the additional function to control the air temperature and air quality, if not, a night light and white noise. Their products pale in comparison to ours, which has all the functions in one system. With all the details established, we can now move on to the component section. We will start with my component, the LED light. The LED light is basically a bulb that illuminates an area. The LED bulb we are using in this project has adjustable brightness, and is turned on or off according to the data sent by the light sensor. By using the MQTT subscription, the lux value is obtained by the Arduino JSON library. I managed to deserialize the JSON file into a string using the parse JSON method to obtain the lumens value from ThinkSpeak every 15 seconds. From there, we used the growth manual and created an if-else loop to control the bulb's brightness via PWM signal. In this case, we use PWM signal because we need to use analog write to control the LED brightness, and we need a digital signal from ThinkSpeak MQTT. When a lux value is received from the ThinkSpeak MQTT, the MKR board lights up green, otherwise it will light up red. When the lux value obtained by the light sensor is 95, the LED light will light up at maximum brightness. Between 95 and 195, the LED light brightness will adjust, and when the lux value is above 195, the LED will switch off. This is my RGB I/O map. Zhiyang will now take you through the light sensor component.
Thank you, Ryan. Now I will be talking about the light sensor. The light sensor detects the light intensity in the room and controls the brightness of the LED in real time. When the room is dark, it will signal the LED to light up, and when the room is bright, it will signal the LED to off. The light sensor reads an analog value, which we will then convert into lux using reference from the growth specification sheet. We will then use interpolation to get a more accurate reading. The light sensor will then send the lux value to ThinkSpeak using MQTT every 15 seconds. In order to debug the light sensor, onboard LED will be implemented. When MKR is connected to MQTT, the onboard LED will light up green. If it's not connected, it will light up red. As mentioned by Ryan, these are the lux values we set to control the LED lighting. Next, I'll pass my time to Jingdao, who will be talking about the LCD display.
Thank you, Alex. Hello, my name is Jingdao, and I'm in charge of the LCD display portion in the system. Hence, allow me to delve into the intricacies of the LCD display, which is a pivotal information within our system itself. Its primary function is to relay essential information to the user sourced from various components and sensors. As you can see over here, we have the temperature sensor readings, the brightness level, the LED light mode, the fan switch, and the music. It leverages from REST API, which retrieves the data from 4 different fields in ThinkSpeak. It has a response time of a mere 15 seconds. Moving forward, we recognize the potential for the further enhancement through the adoption of a more robust and efficient server infrastructure, which we can reduce the response time even further. Additionally, a RGB indicator has been incorporated to signify the connectivity status of the Wi-Fi system to the MKR WiFi1010 with red showing that there's no connection and green indicating successful connectivity. Now, let's delve into the specifics of the reading displayed by each component. Each reading is displayed for up to 5 seconds before transiting in a loop sequence. First, the temperature reading presents the ambient temperature captured by the temperature sensor and showcased on the display itself. Following this, the brightness reading is displayed with light sensors converting lux value into actionable insights. The display dynamically adjusts, indicating various levels of brightness that is being shown through the LED itself. So when the LED is on, we can have various modes such as high, medium, and off. So all these are being adjusted accordingly based on the brightness reading value. Subsequently, the fan reading sourced from field 3 in ThinkSpeak determines the operational status of the servo motor-based fan. Lastly, the buzzer, which functions as a music player, employs a similar methodology with an added feature of RGB background illumination to enhance engagement, especially for our target audience, which is babies. Without further ado, I'll now pass the baton to my colleague Qifeng, who will elaborate on our innovation approach to the buzzer component. Thank you.
Thank you, Jingdao. Now I'll be presenting the component buzzer. Buzzer is one of the component or sensor that can play different music by adjusting the frequency of the sound. Since we can adjust the sound and it's a baby monitor, we decide to play the music Twinkle Twinkle Little Star as a lullaby. Next, I'll be talking about the TS MQTT function. We receive data from ThinkSpeak Field 4 using MQTT for every 35.5 seconds, since each node of the Twinkle Twinkle Little Star is split 0.5 seconds each. Next, the RGB lighting. When we receive the GUI user input indicating 1 from Field 4, the light will turn on, indicating that the music is playing. Next, the LED light RGB I/O map. From the user input or from Field 4, indicating 0, it will send data to the MKR board, which means that no RGB is being light up and there's no music is being played. And when the GUI indicating 1, sending to the MKR board, the red RGB will light up and the music will be playing. Next, Tonghui will be presenting the temperature sensor.
Now I'll be talking about the temperature sensor. The temperature sensor is a key component in our baby monitoring system, playing an important role in continuously monitoring the room's temperature to ensure a comfortable and safe environment for the baby. It's crucial for our system to have a real-time temperature data, which allow us to make automatic adjustments and keep the room climate ideal. The sensor is designed to be both sensitive and robust, adept at precisely detecting even minor temperature variations. Its level of accuracy is vital for the well-being of the babies, as their comfort is greatly influenced by a stable and suitable room temperature. Moving on, let's talk about the functionalities and integration of these temperature sensors. First off, the sensor is responsible for transforming temperature reading into a readable format. These readings are sent to ThinkSpeak Field 1 via MQTT every 15 seconds, ensuring that we always have the most current information. A notable aspect of this system will be the RGB lighting response. When the room's temperature goes above 25 degrees Celsius, a red RGB light is triggered as a warning sign. On the other hand, if the temperature falls below this level, a green RGB light illuminates, signaling for a cooler temperature. This seamless integration of the temperature sensor into our IoT system significantly enhances the responsiveness and the efficiency of our baby monitoring system. The sensor doesn't just relay crucial temperature data, but it also activates other system components such as the fan, which in this case will be our servo motor, to help maintain the most optimal room conditions. Here will be our sensor RGB I/O map.
Now I'm going to talk about the servo motor in our project. The servo motor is a key component that regulates the temperature accordingly because there is a fan that's attached to the servo motor. And now I'm going to talk about the features and the purpose of it. So the servo motor will turn on and off when prompted by a temperature sensor. So when it's above 25 degrees, the servo motor will turn on to cool the room itself. And if you might ask us how we do that, through ThinkSpeak integration, the servo motor will be able to read the temperature sensor's values in the field value itself. And moreover, you'll be able to turn on and off when prompted by the fan switch in the user interface. So whenever the user feels like turning on the fan, he can switch it on through the mobile app. So now I'll be talking about the LED light mode in the servo motor. As you can see in the RGB I/O map, when the conditions are met, like I said earlier, if the temperature is above 25 degrees or when the user decides to turn on the fan, the LED will turn green as the servo will spin. However, when the servo stops, the LED will turn red to show that the servo is not moving anymore. This is the graphical user interface. As you can see, when the fan is on, there is a different dialog. For the music, there's a different dialog. Depends on the music that's being played. And the home interface itself just shows "Welcome to Baby's Monitoring System." So to summarize this whole project, these are a few key innovations. First of all are the components to able to be automatically turned on and off the light and fan, and the usage of the buzzer to play music to calm down the baby and entertain it as well. Moreover, using Thunderbird, we'll be able to create a user interface, an app for our users who can control all these components remotely. So there were definitely some challenges. The first challenge would be unable to send data via MQTT, and our solution was to create individual MQTT ID and password for each of those components. But there are future improvements that we can make for this project. One of it will be to install an aircon system, because after all, we stay in Singapore and it's a pretty hot and humid country. So instead of just using a fan through the servo motor, we can also install an aircon component. And we can use MQTT for all components, as some of them we're still using REST API, as we were not able to integrate MQTT into it. And instead of using a 180-degree motor, we like to use a 360 motor for the fan because it simulates better. That'll be all, and I hope you all learned a few things of our project today. Thank you.